Greetings, it's Paul Bamberg with a rather short introductory video for Class 24 of Math 117. So far we've talked about call options only in conjunction with share prices or scratch tickets, but in fact any situation where you have a martingale lends itself to options, and an interesting example is casino gambling. Suppose you're a casino owner and you are mildly worried that some very lucky bettor is going to break the bank, that you won't be able to pay him off when he cashes in his stack of chips. In that case, a reasonable thing for you to do is to buy an option that will let you purchase the bettor's stack of chips for a fixed amount, K, just before he cashes them in. So that if, say, you have only $2,000 available to pay off, you can get an option that will let you buy the stack of chips for $1,500. Most of the time, this will not be necessary to exercise, so it shouldn't be too expensive to buy. And the question is, what's the fair price? Well, if the bettor is going to leave after playing T spins of the wheel at roulette, it's easy to write down a formula for the fair price of this option. It's the expectation of your stack of chips after T spins of the wheel, X sub T, minus K, the strike price. But the plus means, of course, that we only count situations where your stack of chips has more than K chips in it. You can work this out by brute force if T is a fairly small integer. The catch is that you have to work backwards from the last spin of the wheel to the next to the last, and finally work all the way back to the starting position. This is best done by computer. However, in this case we have a convergent martingale, and there's a simplifying situation. If the bettor is going to keep betting until he either goes broke or has M chips, then we have a limit random variable, x infinity, which almost surely has the value M or the value 0. I remind you why it's almost surely. It is possible that you can keep winning, losing, winning, losing, winning, losing, and neither go broke nor get up to M chips. But the probability of that event is 0, so we don't have to worry about it. And then, since the random variable x infinity has only two values with probabilities greater than 0, this expectation is easy to calculate. You can play with this idea in examples. So now that we've got this idea of a call option, we can take the seller's point of view. Suppose you've sold a call option to a bettor. In that case, this bettor is likely to do very well if the stack of chips is large, and you want to hedge against this. How do you do it? Well, you make bets the same way the bettor does. So if the bettor is successful and this call option becomes valuable, you will also make a profit. If, on the other hand, the bettor is nearly going broke, the probability that this call option will be worth exercising becomes very small, so it's reasonable you will want to make only small bets. On the other hand, if the bettor is doing very well, you'll make large bets. So this is very similar to the situation with stock options, where the amount delta, the fractional share that you buy, depends on how things are going. If a call option seems likely to be in the money and you've sold that call option so you're liable for it, then you own a rather large amount in the underlying security. If, on the other hand, the call option is likely to be worthless, you own almost nothing. Casanova is famous in history as a ladies' man, but it turns out that he was also a gambler and played the martingale. These quotes I found in Grimet and Sturzacher's Elementary Probability. So here's one from 1754 when he went to Venice. Playing the martingale, constantly doubling my stake. Remember, this is the classic martingale where you keep doubling your bet each time you lose, and eventually you come out one chip ahead. I won every day during the rest of the carnival. I was fortunate enough never to lose the sixth card, and if I had lost it, I should have been without money to play, for I had 2,000 sequins on that card. I congratulated myself on having increased the fortune of my dear mistress. So Casanova is aware of the perils of the classic martingale. You have a very high probability of losing one chip, but a small probability of going bankrupt. And indeed, a few days later he writes, I still played the martingale, but with such bad luck that I was soon left without a sequin. As I shared my property with my mistress, I was obliged to tell her of my losses, and at her request sold all her diamonds, losing what I got for them. She now had only 500 sequins. There was no more talk of her escaping from the convent, for we had nothing to live on. Next time, we're going to approach the Black-Scholes formula differently in terms of perfect hedges without ever mentioning probability. And with that in mind, I want to review the hedging strategy for call options like scratch tickets. This is the special case where something evolves from one state either to a higher price or a lower price. It's one step of a binomial model. It might take place over a time interval of some finite length, t, which means collecting or paying interest is a consideration. And with our standard notation, we let capital S denote the price at the start of the interval. Either it goes up to S times U or down to S times D. And a call option, similarly, will evolve so that it either has a higher value, which I'll call V plus, or a lower value, which I call V minus. Suppose we've sold such an option and we want to hedge against the possibility that its value will increase. How do we do this? We buy some shares in the underlying security. Since delta is getting used in conjunction with delta t, delta x, and so on, I'm going to switch notations and call this theta. Deneen does this also, and I really wish he'd done it earlier in the book. So, what happens if the price goes up? Now we are liable for the higher value, V plus, of the option, but we've made a profit. We bought theta shares for a total price of S theta, and the value went up from S theta to S theta U, so our profit is S theta times U minus 1. What happens if the price goes down? Well, the good news in that case is we're only liable on the option for a lower amount, V minus. On the other hand, we bought S theta shares and we incurred a loss equal to S theta minus the lower price, S theta D. So we've got a loss of S theta times 1 minus D. How do we determine theta? Well, the requirement is that our financial position is independent of what happens to the share price. And notice, we are comparing things all at the same time. So the issue of interest doesn't arise in this calculation. We say, in the up case, our liability is V plus minus the profit, S theta times U minus 1 that we made. In the down case, our liability is S minus, enhanced by the loss of S theta times 1 minus D on the shares that we bought, or V plus minus V minus is S theta times U minus V, and we have a very useful formula. The number of shares required to hedge our position, which we'll call theta, is the difference in option value, V plus minus V minus, divided by the difference in share price, SU minus SD. You've, in effect, worked out this formula from scratch several times in the past, but from now on, you can just go ahead and use it. Interestingly, we've never explicitly mentioned probability in doing this calculation. So now we can calculate the fair price of an option. This fair price is the price at which we should sell the option, and the proof that it's a fair price is, having sold the option for this amount, we can devise a hedging strategy that guarantees that eventually we will pay out precisely that amount that we received. We're doing this just for one step, and we can either consider the up case or the down case. We've already chosen theta, so that the result is the same in both cases. So let's do the up case. In the up case, the option now has a value V plus, but we made a profit of S theta times U minus 1 on the shares we bought. However, some time elapsed. We had to borrow money to buy those shares, and $1 borrowed turns into e to the RT that we have to pay back. So we have to pay interest equal to S theta times e to the RT minus 1. This is easy to overlook in practical calculations, but it's the only place that the issue of interest rates and discounting enters the analysis. So let's figure out the discounted net liability. Okay, e to the minus RT, that's discounting from time t back to time 0. V plus, our liability because the option now has a higher value, minus S theta times U minus e to the RT. That's the profit on the shares minus the amount of interest we had to pay on the money that we bought them. We have a formula for theta. It's V plus minus V minus over S times U minus D. So this ratio is equal to S theta. Now let's put everything over a common denominator of U minus D. There's V plus times U minus D over U minus D. That accounts for that term. And now we can split this up into two terms. The one involving V plus is multiplied by e to the RT minus D over U minus D. The one involving V minus by U minus e to the RT over U minus D. And you say, I knew it all along. This is the probability that the price will go up to the higher value. This is the probability that the price will go down to the lower value. But we got this result from pure hedging considerations without ever mentioning probabilities. And next time we are going to exploit this idea to take a different approach to the Black-Scholes formula. But for now, we're done.